last concept we'll take a look at here concerning graphs, at least for now, is the concept of symmetry. So we generally consider graphs to have the potential to have one of three types of symmetry. They may have none of these, but it's possible that we could see x-axis symmetry, y-axis symmetry, or what we call origin symmetry, or it's often referred to as point symmetry about the origin, or just point symmetry. But starting with x-axis symmetry, we can see the picture here. And so the idea is the x-axis is acting as a mirror line for our graph. So we have a reflection of the graph on either side of that x-axis. And so that's what we see in the diagram in front of us. From an algebraic perspective, what we're looking for is this idea that for the same input value x, we are going to get two outputs, a positive and a negative of the exact same value. So if I plug in 2, I'm going to get 3 and negative 3 out as an output. If I plug in 7, I might get 1 and negative 1 out as an output. So for the same input, I get both positive and negative outputs of the same number. And so we can test for that in an algebraic way using the rule that we see here. If we can replace y in the equation with negative y, and we basically get back to the original equation, then that's an indication that the graph of this equation will have x-axis symmetry. And so we can see that, I think, pretty easily here. If I replace y with negative y, and then everything else stays in place, well, negative y squared, negative y times negative y becomes positive y squared. So we indeed end up with our original equation again. And so that verifies algebraically that the graph of this equation, if we were to plot it out, would indeed have symmetry about the across the x-axis. The x-axis would act as a mirror line. It should come as no surprise then that y-axis symmetry means that the y-axis is acting as a mirror line. So the graph is being cut in half into two identical pieces by the y-axis. And so we can see that in the parabola that's centered on the y-axis. If that parabola was centered over here, then we would not have y-axis symmetry. The graph would have symmetry. There would be an axis of symmetry that we could put in, but it would not have y-axis symmetry because it's not the y line that's cutting that graph into two equal parts. And just like with x-axis symmetry, we have an algebraic test that we can use, and so it's just the opposite. If I can replace x with negative x in my equation and end up back where I started with my original equation, then that's an indication that I have y-axis symmetry. And so we can see that here as well. So if I stay with y equals the square root of 9 minus negative x squared, so now when I square negative x, I get negative x times negative x equals positive x squared, but I'm still subtracting it here. So I am indeed going to end up with y equals the square root of 9 minus x squared when I'm all said and done. And so we can see that we ended up with the exact same equation as our original. So we've confirmed algebraically that the graph of this equation would end up having y-axis symmetry. And then our third and final type of symmetry, origin symmetry or point symmetry, or it can be referred to as rotational, shouldn't have left that off, symmetry, rotational symmetry, and that's always about the origin. And so the best way to kind of imagine this one is if we rotate our graph, if we were to spin our paper 180 degrees, would the graph fit right back on top of itself? If the answer is yes, then we say that we have origin symmetry. If it doesn't fit on top of itself, then it does not. So if we look at these first two examples, if we were to spin the paper 180 degrees, clearly we would not fit back on top of ourselves. This one would now look like this. Here, for the parabola, we would have an upside down parabola if we flipped rotated the graph 180 degrees. But on this one here, indeed, if we rotate, if we just spun our paper around, we would see the exact same graph. From an algebraic perspective, it's a little bit different than the other two. So now, because opposite inputs are supposed to yield opposite outputs, what we're going to do is we're going to replace both x and y with their opposites. So I'm going to swap out x for negative x. I'm going to swap out y for negative y. And so then if I do that and I can work myself back to my original equation, then I know that I've got origin symmetry or this rotational symmetry. So let's do just that. So I'm going to replace y with negative y. I'm going to replace x with negative x. Just have to make sure I put in a set of parentheses there. And then minus negative x here. So if we keep on going, we're going to see we've got negative y equals, now negative x cubed is negative times negative times negative. So I'm going to get a negative and then x cubed. And then here we've got minus a negative, which becomes plus, whoops, not 1, but a positive x. And so now, doesn't look exactly the same at this moment, but if I divide everything by negative 1, then we can see that we are indeed going to get back to where we started. Negative y will become y, negative x cubed will become positive x cubed, positive x will become negative x, and so we indeed can get right back to where we started. So that's our test for origin symmetry. So let's deploy those algebraic tests for symmetry to the examples that we see here. And the nice thing is, once we confirm one type of symmetry, we can rule out any others. So if we start with the first one, I'm going to start and say, all right, let's replace y with negative y. So since that's pretty low hanging fruit for us, pretty easy to do. If I replace y with negative y, do I get back to my original equation here? And clearly I don't. If I was to try to divide everything by negative 1 to turn this y, negative y into a positive, well then everything else would turn into a positive. So I can eliminate x-axis symmetry from consideration. Now what about if I test for y-axis symmetry, meaning replace x with negative x? So I've got negative, and then in place of x, I'm going to put negative x squared. So we just have to be careful that we put that inside of parentheses. So everything else stays exactly the same. It's just the x that gets swapped out for negative x. And so I'm going to have negative x squared. It's going to be negative x times negative x. It's going to give me positive x squared. But then I still have this negative out in front, so I'm still going to end up with negative x squared here. And I still have this minus 2. And so indeed, we can see that we've got the exact same equation as what we started with. And so this confirms for us that we have y-axis symmetry. And then immediately, just to prove the point, if we were to plug in negative x and negative y, I hope it's not a heavy lift, we basically would have gotten the exact same thing on the right-hand side of our equation, but we would have had negative y on the other side, which of course means we wouldn't have ended up back with where we started. So y-axis symmetry is all we've got. For the next one, if we replace y with negative y, start in the same place that we did last time. So negative y equals absolute value of x plus 3. Clearly we don't have the exact same thing. If I was to divide everything by negative 1, I would not get back to my original. So I do not have any x-axis symmetry once more. Now what about if we replace x with negative x? So if we say y equals the absolute value of negative x plus 3, well, if we remember, absolute value just makes whatever is on the inside positive. So if I take a number and I plug it in for x, even with a negative sign in front of it, as soon as I hit it with the absolute value, it's going to turn it back into a positive. And so that means I'm going to end up right back where I started. So here again, I've replaced x with negative x. It got me back to the original equation that I see in front of me at the beginning. And so therefore, we once more have y-axis symmetry. For our last one, again, hopefully it's easy to see. Replacing y with negative y is decidedly not going to get us back to our original. If I divide both sides by negative 1, I'm going to get y equals negative root x minus 3, not the same thing. If I replace x with negative x this time, I'm going to have y equals the square root of negative x minus 3. I have no way to being able to get back to my original equation here in this case either. So I do not have any y-axis symmetry. And so then our last test is to replace y with negative y and x with negative x. So negative y equals square root of negative x minus 3. And then once again, hopefully we can see that there's no pathway for us to get back to this original equation. Dividing by negative 1, we already showed that that's not going to do it. And so as a result, this one does not have any symmetry. So, as we can see, we don't always have symmetry in our graphs. It's only sometimes. The way we can test for it is either to use these algebraic tests, or of course, if we're familiar with what the graph looks like, that too can be useful for us in determining what type of symmetry a particular equation is going to have.